السلام عليكم ورحمة الله وبركاته والصلاة والسلام على سيدنا محمد وآله وصحبه أجمعين. Today we will talk about the reaction rate, about tahsili chemistry, of course. And what about the reaction rate? What do you need to know for the reaction rate? So first we need to know about the average reaction rate. How to calculate the average reaction rate? And to calculate the average reaction rate, we have two formulas. We have two formulas. The first one is the change in the concentration of the reactant, one of the reactant, over delta T, or the change of the concentration of one of the product over delta T. If we have a reaction like A plus B will give you C. So here we can write the formula of the average of the rate by the change of the concentration of A over the change of time, or the change of concentration of P over time, or the change of the concentration of C over time. But for the reactant, we know that the concentration of the reactant will decrease by time. So if we calculate the change of the concentration, it will be a negative sign. So here we need to add a negative because the rate will be always a positive sign. And the unit for the rate would be mole per liter second, which is the unit for the concentration, which is mole per liter. And the time, of course, will be with second. Sometimes the time could be with minutes or with hours. It's okay. Here, if we want to calculate it, so it will be the final concentration of A minus the initial concentration of A over delta T. And of course, again, we need to add a minus or a negative sign here, or it will be the final concentration of B minus the initial concentration of B. And again, we need to add a negative sign, or it will be with C. So it will be the final concentration of C minus the initial concentration of C over delta T. And by this way, we can calculate the average rate for a reaction. So let's take an example. If we have a reaction, H2 plus Cl2 will give you 2HCl. And we know that the concentration of H2, we have the initial concentration, it was 0.03 molar or mole per liters. And we have the final concentration of H2, it's 0.02 molar. And the time delta T is 4 seconds. So if you want to calculate the average rho, so it will be the final concentration, which is 0.02 minus the initial 0.03 over 4 seconds. And we know this one is a reactant, so we should add a negative because the rate will be always a positive sign. So it will be 2.5 times 10 to the negative 3 mole per liter second, or molar per second. Okay, so this is how to calculate the average rate. Now, how to explain exactly why some reaction will be with a high rate and some other reaction will be with a low rate. For this explanation, we have a theory, and this theory is called the collision theory. So the collision theory is just to try to explain for us why some reactions will be fast and some reaction will be slow. We have three assumption for this theory. The first, from its name, the collision, so it means all reactants should or must collide with each other. So the reactant molecules should collide with each other in order to form the product. And when they collide, they need to have two things. The first one is correct orientation. So the orientation should, when they collide, they should collide in a correct orientation to help us to help them to form a new bond and break the old one. And with sufficient energy. Of course, when they collide, they need to have a sufficient energy, and this sufficient energy is called activation energy. Okay, so why the sufficient energy? Why activation energy? Why do we need activation energy for? So if we have two molecules, or one which is A2 and B2, and they will collide with each other. So here, if they have a correct orientation, so A will collide with B and A will collide with B in order to form this bond and break the bond in the reactant. So when they collide, actually, if they have sufficient energy, they will form this structure. This structure is called activated complex. And this activated complex is unstable, a transition state. This activated complex to reach this activated complex, so the molecules here or the reactant should have the activation energy. So as they have the activation energy, so they will form this activated complex. And actually this activated complex is a very important part in the reaction. If you don't form the activated complex, so you will not form a product according to the collision theory, of course. So in order to form a product, you should first form the activated complex. Okay, when they form the activated complex, which is a transition state, now they are breaking the old bond and forming new bonds here. So they will form AB and AB. Okay, so we need to know the definition for the activation. Energy. So what is the activation energy? Activation energy is the minimum amount of energy required to form the activated complex. So the energy required to form this activated complex will call the activation energy, and this activation energy will be written as E. And here we have an inverse relationship between the activation energy and the rate of the reaction. It means that the higher the activation energy, so they can't reach or they can't form this activated complex so easily. That's why the rate will be very small value. It means that the reaction will be slow. And again, we need to draw the reaction or the energy diagram for the reaction. So here for the x-axis, we have the reaction progress. And here we have the energy. Okay, so here I will start with the reactant. This is the reactant. So this is the place of the reactant, means this is the energy of the reactant. Okay, and here this is the product. Means this is the energy of the product. So here the energy of the reactant is more than energy of the product. In order for the reactants to form the product, so first they need to reach or form the activation or activated complex. So this is the condition for this reaction to happen. So they need to form the activated complex, and then they will form the product. So they need to reach to this peak, and then they will form the product. The energy between the reactant and this point is the activation energy. Okay, this will be the same here also. We have the reaction progress here and we have the energy here, but I will change the energy and of the product and the reactant. Here, this is the energy of the reactants, and this is the energy of the product. Okay, and again, for the reactant to form a product, they need to reach the activated complex. So they will reach this point, and then they will form the product. Where is the activation energy from starting from the reactant to the activated complex? This will be the activation energy, E. What is the difference between the two graphs? For the first one, we have the reactant energy. So the energy of the reactant is higher than the energy of the product. Okay, it means this reaction is exothermic. And for the second one, we have the energy of the reactant is less than the energy of the product. It means this one will be endothermic. Okay, sometimes he will give you a graph with different value for activation energy, like this one. We have different reactions here. This is 1, 2, 3, and which one will be the fastest one? Which one will be the slowest one? Okay, the fastest one will be with the lowest activation energy, and this is activation energy here. If we're starting from the reactant, so it will be this one, and this is activation energy, and this is activation energy. So it means that one with the smallest value for the activation energy, so one will be with the highest rate, so one will be the fastest one. Okay, next we need to know about factors affecting rate of the reaction. We have 5 factors. The first one is the concentration of the reactant. And here we have a direct relationship between the concentration of the reactant and, let me erase this one, and the rate. It means that the higher the concentration, the higher the rate, and this reaction will be fast. Okay, so if we take 2 solutions, one with 1 molar and the other with 2 molar, so 2 molars with high concentration, so this one will be fastest, this one will be will have a high rate. 2, temperature, and again we have a direct relationship between temperature and the rate. The higher the temperature, the higher the kinetic energy of the molecules, they will collide with each other, so they can form the activated complex, so the rate will be higher, it will be faster. Okay, 3, surface area. So for surface area here, I'm talking about surface area, we're talking about solids only. So we're taking a piece of metal, and here we're taking pieces, and here we're taking powder. So what is the difference between the 3 parts here, of the 3 kinds here? If you can make the piece of your metal as small part as possible, so this will give you a high surface area. So the high surface area will be the powder, and this one will be number 2, and the smallest surface area will be number 1, which is only 1 piece. So here we have the surface area has direct relationship again with the rate. It means the larger surface area, the highest the rate. So the powder will be with highest rate because it has the highest or the larger surface area, and number 2, it will be the small pieces, and the third or the smallest surface area, and again it will be the slowest or the smallest rate, it will be number 1, which is 1 piece. 4, nature of reactants. When we talk about nature of reactants, we talk about element like Al, Zn, Ag, and to compare between the speed of the reaction of each one of them or the rate of the reaction for all of them. So we need to go to the activity series. But of course, you are not going to memorize the activity series. When we compare here, when we ask about this part, he asks only about Zn and Cu, which one is the reaction, which one will be faster. So Zn is more reactive than Cu, so the reaction of Zn will be more faster than Cu. 5, catalyst. And catalyst is just like materials that can be used to or to proceed the reaction with a small activation energy. So what the catalysts do, again, they increase the rate because they have a inverse relationship with the activation energy. Using the catalyst will decrease the activation energy for this reaction. That's why it will have or will increase the rate. If we go back to this graph again, and we want to draw, we have 2 paths here. The first path, which is the red one, with reaction without a catalyst. If you want to draw a reaction with a catalyst, so we will draw the same path. We will have another pathway, and this pathway with a small activation energy. So the activation energy here will be smaller. That's why this action with the catalyst will be faster. And if you draw it here, it will be the same, and the activation energy again will be smaller. So this reaction with a catalyst will be faster. So using a catalyst actually will decrease activation energy. That's why it will increase the rate. The last part here is rate laws. If you have a reaction like A will give you B. Okay, the rate law will be written like this. R will be equal to K, and K is a constant, times the concentration of the reactant, only the reactant. So for the average, we used sometimes the reactant or the product according to what you are given. But here you need only to use the reactant. We can't use the product in the rate laws. So R, which is the rate, will be equal to K, which is constant, and this constant will be different from one experiment to the other one, and times the concentration of A, which is the concentration of the reactant, to the power of N. And N is not equal to A. So N is not taking from the coefficient, is not the coefficient from the equation. You can take N from your equation, okay, because it's not the same. N is determined by the experimental value or experimental data, and N is called order of the reaction or the rate order. And here it's for A, so it will be order with respect to A. Sometimes for some reactions, we will have more than one reactant. So it can be A plus B will give you C. So we have two reactants here. So the rate will be A equal to K times the first reactant to the power of N to the second reactant to the power of M. Sometimes they could have the same order and sometimes not. So N, which is the order of the reactant, it's a whole number. So it can take 0, 1, 2, 3, 4, and so on. Okay, if it's 0, it will be 0 order. It's 1, it will be first order. If it's 2, it will be called second order, and so on. So if it's for A only, like this one, so if we're talking about the second reaction here, we have Fn equal to 1 and B, which is M, equal to 2. So it means that the reaction is first order with respect to A and the second order with respect to B. But we have something called overall rate for the reaction. The overall rate for the reaction will be N plus M, and this will be 3. This will be the overall rate. So in order to calculate the overall rate, so we need to add all the exponents that we have for the reactant. Okay, so again, we have R. I will take the simplest one, which is A to the power of N. Here we have R, which is the rate, and the unit for this R will be mole per liter, and second, and of course the unit for A, it will be mole per liter only. Okay, so now what about K? Actually, K is a constant, and again it will be changing or to be different according to the experiment, and for one experiment or for one reaction it could be changed with temperature only. So the only factor that can change the rate constant, it will be the temperature. It will be temperature. But what about the unit? Unit of K is a very important part for tahsili. You need to know how to derive this unit. And actually we have a formula. K, the unit of K will be L per mole second. And here we will have X minus 1 and X minus 1. And what is X? X is the overall rate for the reaction. So if he told you that this reaction is a first order, so it means the unit of K will be L 1 by 1 minus 1 mole 1 minus 1, 0. So this will be 0 and this one will be 0. So it will be 1 over second if it's first order. If it's a second order, so the unit of K will be equal to L 2 minus 1, it will be 1, mole 2 minus 1, 1 second. So it will be L per mole second. And if it's third order, so it will be liters square, mole square second. Okay, the last part, we have something called zero order. So what is zero order? Actually, zero order where the change or the change in the concentration will not affect the rate, because the rate will be only equal to R equal to K. Because the concentration will be to the power of 0, it means they are not here. They are not found in the formula. So R equal to K, it means they are not, the change in the concentration of the reactant will not change the rate of this reaction. Let's do some problem for tahsili. Okay, first, change in reactant or, okay, let's draw. Change in reactants or product concentration per unit of time. So of course, this one will be the reaction rate. This is the definition of the average reaction rate. Okay, for 2, calculate the reaction rate for H2 plus Cl2 will give you 2HCl if the initial concentration of hydrogen is 0.9. This is the initial, and and they change it to 0.2. This will be the final 0.1 in 4 seconds. So it will be 0.1 minus 0.9 over 4, and it will be always with a positive sign. So it will be 0.8 over also it will be 0.2. What is the following is not from the collision theory. And enough energy to collide. Okay, this is right. Okay, correct orientation, also right. Constant temperature, we didn't say constant temperature. Actually, this is not from the collision theory. Reactant must collide. So actually, so the answer will be this one. So the activated complex is unstable. Transition state, which is unstable. So it will be this one. This one is very important. Here you need to know the graph and each part of it. Okay, so which number represents activation energy? So again, let's go for each one of them. For 2, this will be the reactant. 3 is the activated complex, 4 is the product, and 1 is the activation energy. And exothermic reaction product energy is than the reactant energy. So if it's exothermic, it means the reactant will be higher energy. It means that the product of the energy will be less than. And endothermic, of course, it will be the opposite. The reactant will be less. Which of the following is not affecting the rate of the reaction or the reaction rate? We know that the concentration of one of the 5 that we said, and again, the nature and temperature, but nature of the product, we didn't say this one. So this one is not affecting the rate of the reaction. Which of the following increase the rate of the reaction? Decrease the concentration. Okay, so we said that the concentration have a direct relationship with the rate. So if you change the concentration by increasing the concentration, so the rate will increase. So it means this one was wrong. Increase the concentration, yeah, increase the concentration would increase, of course, the rate. The product, the concentration of the product actually doesn't affect the rate of the reaction. Okay, burning 1 kilograms of sawdust, okay, is faster than burning 1 kilogram of wood. Why? This is because of the surface area. This is the surface area will be a large surface area than 1 piece of wood. So it means when surface area it will be increased, the rate will be increased. So this one will be the surface area. Which enzyme is more effective? To be more effective, it means it's more faster. The reaction rate will be more, the reaction will be higher, it means it will be faster. So it means that with low activation energy, so it will be number 4. And again here, 4 enzymes are used in different tubes. Which one of them will be with highest rate? So highest rate, it means you should have lowest activation energy. So the lowest activation energy will be 2. Okay, the reaction rate constantly change only with temperature. So reaction rate only will change with the temperature. The unit is not used for the reaction constant. So the reaction constant mainly should take the formula liters per mole second, and the liter and mole could take a different exponent, okay, starting from 1 to 2, 3, 4. And we could have, and of course, also 0, because we could have S minus 1 if we have L per mole second. This is the formula here, and this will be X minus 1, and here X minus 1. So this one could be a 0 or 1, 2, 3, 4. So we should have this. If we have 0, so it will be S minus 1. So this one will be right. This one we have L and mole 1 and 1. You have 2 and 2. Here we don't have second. So this one is not used for the reaction constant. Exponent of A is not the coefficient. So exponent of A is not the coefficient, it's the order of A. The overall order for this reaction, so we need only to add the exponents, or sum the exponent 1 and 2, it will be 3. If the substance A is 0 order, so its change its concentration will not change the rate of the reaction. So it will do not affect the rate. Which unit is not for the reaction rate? So again, the reaction rate should be with molar per second or mole per liter and second. And the only thing that you can change here is the second. So it could be minute, it could be hour or second. So this one is right because this will be per second. This one is right, okay. And this one also is right, but this one is wrong because here he wrote molar dot second or molar time second, not per second.